Now we discuss a very important fiber manufacturing technique, which is known as electrospinning. So anybody who has worked in fiber manufacturing, not just carbon fibers, but any fibers, polymer fibers for various biological applications, drug delivery applications, membrane fabrication, anybody who has prepared fibers has definitely performed or at least heard of electrospinning technique at some point. This technique is indeed also commercially used. It has been used for over 5 decades. So this is a very well-known technique, and that is why you also have advanced versions of it. And industrially for carbon fiber fabrication, this is the most commonly used technique. Okay, so this is how the electrospinning setup looks like. Okay, so this is a basic schematic. What do you see here? You see that there is some sort of a syringe where I have a polymer solution, or it can also be a polymer melt. So you have a syringe-like structure. You can call it a spinneret. And then on top of that syringe, there is a needle. Needles are made of metal. Syringe can be of plastic, but needles are typically made of metals. Now this syringe, you can also attach to a syringe pump just to push the solution, push your polymer out. Okay, so now you have a needle, and on the other side there is something known as collector. These are your two electrodes. Okay, now what you're doing is, as soon as the polymer comes out of the needle, you are creating a very high voltage difference. And because of these electrostatic forces, now your fiber, your the droplet that was on top of your needle will ultimately become very unstable, and a fiber jet will come out of it, and that fiber jet then further splits into thinner and thinner fibers, depending upon also the nature of the electric field. If you draw the electric field lines inside your chamber, and then you will have this further splitting of fibers, and then you will collect them onto the collector. So it sounds very simple, right? It is indeed very simple. So these are the steps that whatever I have just mentioned, I have also written here. Basic principle of electrospinning. Okay, so you actually apply a high voltage between two electrodes such that you create a voltage difference, a potential gradient. Your collector is grounded. Okay, now you have a polymer solution melt inside the syringe. E1 and E2 are the names of the two electrodes that I have written here. What happens is, when you actually have this very high voltages applied, which are typically in the kilovolt region. So when you apply these high voltages, there are charges accumulated on top of that droplet which is just coming out of your needle. Why is it coming out of the needle? Initially you gave it a little bit push. That is why you needed the syringe pump. So initially you sort of just gave it enough push so the droplet came out and was sitting on the tip of your needle. Now you created the electric field, and because of this strong electrostatic forces, now your droplet, you will see it is a spherical droplet, but then its tip suddenly starts to it comes out. At some point it starts forming this conical shape. This type of cone is known as the Taylor cone. So there is this Taylor cone formation. If you further increase the voltage, what will happen? Now there are so many instabilities. This Taylor cone cannot remain in the conical shape forever. So what will happen is that cone finally leaves a jet at certain threshold voltage, and this jet, as I mentioned, further splits into various fibers. You can actually get nanoscale fibers easily using the electrospinning technique. And in the case of our carbon fibers, whatever fibers we are getting, we are then performing the heat treatment. They're also undergoing certain shrinkage. So it is easier to get nanoscale fibers using this technique. However, you see that you're not collecting individual fibers. You see this image I have made here, fibers on a substrate. So if I have this collector substrate and I have fibers coming from here, what I have on the substrate is sort of a mat, a fabric-like structure. They are not woven fabric. So weaving is something that we call when we are very, in an organized manner, when we are weaving the ropes. These are not woven fibers, but they are randomly oriented. But there are a lot of fibers, and typically you'll have several layers of such fibers depending upon how long did you perform your electrospinning, and you will have these layer of fibers, and that would look like a cloth. So this is how your fibers will look like on a substrate. Okay. What else? Now think of what are the things that you can do with, or what are the parameters that you can control. So number one, you need to control the properties of your polymer. How viscous is your polymer? How much viscoelasticity it has? And now at the end of this lecture, after the 2 slides, I'm going to describe the property viscoelasticity. So that is number one. That becomes very important. It also becomes important, what is the difference between, what is the distance, physical distance between the 2 electrodes. Okay. Also, the characteristic voltage that is just determined by each polymer. So every polymer has a certain range in which this Taylor cone will be formed, and then the jet will be released. So based on the nature of your polymer, you will decide what is going to be your the voltage that you need to apply. So this becomes an important parameter. What is also important when you have the syringe pump, what it is doing is, once a droplet gets consumed, so you make so there was one droplet in the beginning, and you keep on consuming the material, right, as the jet is going and you are collecting the fibers. So now you need to refill. So you need to also then give it a push. So your syringe pump is basically pushing the solution through the needle and refilling and making sure that there is enough material for fiber formation. The flow rate at which these droplets are released. So basically the flow rate of your syringe pump, that also becomes an important parameter. Okay. Now, here you see that I have written something called far field or traditional electrospinning, and then I made this sort of zoomed in structure where I show the Taylor cone. Okay, the one goal of that zoomed in structure was to show you the shape of the Taylor cone, and also you see a gray line there, vertical. That is the collector. What happens? So if you see in this jet that is formed, initially, if you zoom it in, initially your fiber jet is like this one big thick fiber, which then splits further. And it becomes smaller, smaller as we go further. But of course, you cannot go too far from the collector also, because then the voltage difference becomes too low. So there is optimum distance. Again, depending upon what is the characteristic voltage for the polymer, you have that optimum distance between the 2 electrodes. In the case of most of the industrial processes and most of our carbon fiber precursor fabrication processes, we have this distance between 10 to 15 centimeters. That is generally used distance, but you can use anywhere between 5 centimeter to 20 centimeter in the case of the standard or traditional electrospinning, or we just call it electrospinning. That is the standard or common form of electrospinning. But there is then a variation of this electrospinning technique known as the near field electrospinning, where, as the name suggests, the electrode is too close. When you still have this one single thick fiber, if you place the electrode right there, so close to the needle, so you can have higher voltage difference. So it is even at lower voltages. So because the distance is so little. So this variation is known as near field electrospinning. Why would we do that? Because in that case you get the single fiber jet. So in that case you can practically write with that fiber. So then it becomes like a printing technique. You can also move your stage. Rather, don't move the needle or the syringe. You can move your stage, and then in a controlled fashion, if you move the stage, you can perform controlled writing. You can make controlled structures using fibers. However, the disadvantage, of course, is that because this is one thick fiber, it is thick. So that is the problem. It is a thicker fiber. So if you want to get nanoscale fibers, then far field or the standard electrospinning is the one that you can use. Of course, as I said, that if you control the viscosity of the polymers, if you control the elasticity of your polymers, in that case you actually can get you can even pull very long fibers or very thin fibers from certain polymers. In the case of carbon fiber manufacturing, however, near field electrospinning is not commonly used, and for us what is more important is the bulk industrial carbon fiber fabrication. So we only talk about the standard electrospinning. This was just for your information that there are other variations that exist. Okay, now this you will not use for this electrospinning technique is typically used for polymers, but often it is not used for pitch. However, there are papers where people have reported electrospinning of pitch. Pitch is more commonly used or spun using melt spinning. Okay. Yeah, so this is one image of an electrospin fiber mat, and the polymer that was used here is known as polyacrylonitrile or PAN. This is the most common precursor for carbon fibers. That is why I've shown it here. So this is how a mat looks like. So you can see this particular mat was spun on top of a silicon substrate, so silicon wafer. And now you have this cloth-like structure. So if I pick it up with a tweezer, then the entire sort of cloth-like structure comes out. So this is an example. This is how your fiber mat should look like after electrospinning. This is another optimization parameter would be for how long do you want to perform the electrospinning, how thick you want your mat.
So what are viscoelastic materials? You know that viscoelastic materials, they have two components when it comes to their deformation. One is the viscous component and the other one is the elastic component. Okay, what does viscous mean? It means that you have permanent deformation. So this kind of behavior you will typically see from the liquids, and once a liquid is it takes a certain shape, it does not come back to its normal shape. So in terms of deformation, this is the permanent deformation. In the case of elastic materials, however, you have reversible deformation. So it's like a rubber band. You stretch it, it comes back to its normal position. So you know that this kind of behavior you see from the solids. Now the question is, our very viscoelastic polymers, why do they behave like both liquids and solids? So let's take an example of a semicrystalline polymer. You know, in the case of semicrystalline polymers, you have certain either the chain-like molecules or sheet-like molecules of the polymer. They are arranged in a certain fashion, but these crystallites are randomly oriented. Okay, so this is our semicrystalline polymer material. However, what happens is you also have some other polymer chains, maybe entangled a little bit, maybe not, maybe some small ones, some large ones. You also have other molecules of the same polymer which are in the amorphous region of the polymer. So they are able to flow freely or relatively freely. So this free-flowing type material then behaves like a liquid, while this material can actually undergo elastic deformation. What does that mean? That it means it will come back to its normal position. So we have both components. So this is the example where you have semicrystalline polymers. However, what if the polymer is not semicrystalline? In that case, well, we know that polymers have these chain-like molecules and they can be very complex. You can have these chain entanglements which can make very complex geometries. However, again, we have some not so complex geometries as well. We may have also chains that are not all of the same length. So again, we have the same kind of structure. If you take one of these entangled chains and you try to stretch it, then this will try to come back to its normal position because its entanglement points, the chain of the molecule will try to pull it back through the entanglement points. However, this part which behaves like a liquid, this part is, again, this is like a viscous liquid and this can freely flow. So that is why you have both of these behaviors in the case of a viscoelastic material, which are predominantly polymers. Also are pitch and some hydrocarbons, heavy hydrocarbons, petroleum products. They are also viscoelastic. Okay. Now what we need to do is we would like to understand what is the overall deformation behavior of a polymer. So if I draw the stress strain curve, so this is your stress Newton per meter square, and this is the delta L by L. Okay. So in this case, what happens? So you know that for any elastic solid, what happens? You have a stress strain curve that looks like this. Now here, the slope of this line is your Young's modulus. Okay, so also in the case of polymers, what you have is you have this initial elastic region, because we do have some elastic component of the deformation, right? And from here you can also determine the Young's modulus, and in fact that is how the stiffness of polymers is often determined and specified. This is the initial elastic region. What happens after that? In the case of solids, you will have, you will have a yield point after your elastic region is finished. Right after that, what you have is you have a yield point, and then you may have, at some point you will have further deformation and fracture. While in the case of polymers, what happens is you then have a slightly different behavior, and the curve looks something like this, and the fracture actually happens much later. You will have the yield point also in the case of polymers, but in this region, what you have is you have strain hardening. So strain hardening also takes place in the case of metals and other crystalline solids, but the mechanism in the case of polymers is slightly different. What you have here is the strain hardening is taking place because of the realignment or rearrangement of the chains. Okay, so this is your overall, this is overall deformation behavior of polymers. Now let's see if we have some models, some mathematical models to represent this kind of behavior. Okay, so in the case of mathematical models, what do you need? You need sort of two components. You need one elastic component. Let's take a spring. And you need a viscous component. Viscous component is represented by what is known as a dashpot, or it is also called a damper in some cases. Okay, so we have these two components, and now what we are going to do in different models, we are going to connect them as a circuit element, as circuit elements. We are going to connect them either in series or in parallel. Okay, so the first model that we have here is known as the Maxwell's model. Okay, in this model, you have both of your elements connected in series. Okay, so this is your spring and this is your damper. Okay, now before we derive any equation for this model, let's see some very fundamental equations. In the case of elastic solids, what happens? You have the stress proportional to strain, and the proportionality constant is your Young's modulus. Let's call it equation number 1. In the case of viscous liquids, what happens? You have your stress not proportional to the strain, but to strain rate. And here your proportionality constant is eta, or this is what indeed is known as viscosity. Okay, now since this is the component, the first one, the equation 1 is, let's say this is for our spring system, this is for the elastic part, so I will have S, I write S here, and this is the one which is for the dashpot. Okay, so now let's see what is the overall stress and overall strain on the system in this model. So now you can see that the overall stress, let's call it sigma total, that is equal to the sigma on your spring element and also equal to the sigma on your dashpot. However, that is not the case with strain. So the total strain is now the addition of on the this spring plus on the dashpot. So these are the two equations that you have. Okay. Now what we can do here, we can take the derivative of the second equation, of this equation. So let's call it equation number 3. So we have this derivative of this entire equation, the epsilon total because why are we doing that? Because our goal is to find out what is the total deformation of the system, what is the total strain on your system. So that is why we are taking the derivative of this. Okay. Now we need to find out the values of different components. So this is our equation 4. Now from equation 1 and 2 we are going to insert some values here. If we see equation 1, in that case you see that if you take the derivative of this equation 1, what do you get? You get d of sigma s by dt, and that would equal E and d of epsilon s by dt. This is the value we wanted, d of epsilon s by dt. So what is it? This is 1 by E d sigma s by dt. And the second one, the value of the second term, that we can easily get from here. We already have the value. So this is basically sigma d divided by eta. So this is your equation. This is your model. Now you can make some other modifications. You can, for example, sigma here. Sigma is equal to sigma S and sigma D. Both are equal to the total sigma. So you can just replace these terms with sigma T, or you can just call it sigma. But this is basically your equation. You can. This is your model number 1. Okay. So let's talk about model number 2. Model 2, I'm not going to derive it because again it is very simple. The only difference is that here both components are not connected in series, they are connected in parallel. So what will happen is now your stress value will be the addition. So total stress on the system will be the addition of the stress on each component, while the strain will remain equal. So sigma S, epsilon S will equal epsilon D will equal the total epsilon or total strain onto the system. So you can solve this one for yourself. This second model is known as the Kelvin-White model. Okay. Now the model number 3, this is kind of a combination of the two models. You have a spring, and then in series you have this spring dashpot system connected to it. So again you can solve this model for yourself. This model is known as the standard linear viscoelastic model. So standard linear viscoelastic model. So you can solve all these models for yourself. And this is, now the point is that there is nothing like which model is good and which one is bad. It's more about what is the type of your polymer. Do you have what is the viscosity component of in your polymer? What is the elastic component in your polymer? Depending upon that, which will depend of course upon the properties of the polymer, what kind of chains you have and so on. That is how you will find out which model is more suitable for your system. Now I would like to also quickly tell you how do these models actually represent the deformation. So if I apply a certain force onto this polymer for a given time t, so I apply the force and then I apply it I hold it like that and then I release the force. In that case, what will be the deformation? How will the deformation look like according to each individual model? So in the case of your first model, which is your Maxwell model, you will have certain elastic deformation in the system in the beginning. Okay, then there will be a linear change in the properties in the deformation, and then after when you release the force, then what will happen is this elastic part will come back. So whatever is the magnitude of this part will be the magnitude of this part, and then you will have a relaxation. So this is how the deformation will look like as per the model number 1. Now what happens in the case of model number 2? It indicates that there is a certain, so the deformation is not linear, and also the relaxation is represented like this. So this is your Kelvin-White model. This model is very good for representing, for example, creep in the system. Okay, in the case of third model, it looks something like this. So you have an elastic component in the beginning, then you have this kind of behavior. So you do have a certain creep in your system. However, after you release the load, then you have again the same magnitude. You have the elastic component coming back, but then you have a relaxation mechanism. So this is your third model. Okay, so as I mentioned before that, according to the nature chemical properties of your polymer, you can select the model that is suitable for you.